All right. So, now let us look at the equilibrium cooling of an isomorphous alloy. What do we mean by equilibrium cooling? When we are cooling down an alloy from a liquid state to solid state, we are giving sufficient time for the process to follow the equilibrium path. All right. So, that means you are cooling down at a very slow rate. So, that means from the practical perspective this may not be feasible, but when we are studying the equilibrium cooling of an isomorphous alloy is an interesting thing to study, so that we can understand how the microstructures evolve, and then compared to such an idealistic equilibrium cooling, what happens in a realistic scenario, also something that we will look at. All right. So, now let us look at this system. Here we are looking at an alloy which is cool from 35% nickel, which is in liquid solution at point A, and we are actually trying to cool it down. All right. So, when we are cooling it down until this guy reaches up to point B, just above point B it is liquid solution. On this line you will start having two phase region. That means, when you are reaching just this point B around this guy, small nucleus of solid solution start forming. So, that means this you can see these are all small nuclei of solid forming, but then that is you are already in the two phase region now. Now, since you are in the two phase region, you should draw a tie line and say what are the compositions of the liquid and solid phase. So, now you draw the tie line, because you are in the very beginning, the liquid phase, so the composition will be almost same as the original composition, that is 35% nickel, that is what it is shown. But the tie line, whatever initial solid that is formed is very rich in nickel. So, that is 46% nickel, right. You can see this is 46% nickel. So, if you draw a vertical line, that corresponds to 46% nickel. All right. So, you enter the two phase region, and then if you further cool it down, what happens? When you are further cooling it down, let us look at point C. You are still in two phase region, and then you draw a tie line. You have drawn, this tie line is drawn, right. Now, let us look at the compositions of liquid and solid. So, here if you again let me finish this. So, the compositions of liquid and solid. So, this line hits the liquidus at this position. So, that corresponds to 32 nickel. That means, what is happening? Initially liquid was 35% nickel, and then by the time it reached here, the liquid became lean in nickel. That means, nickel composition in liquid is reducing. So, it became 32% nickel, and the solid is also become 46 to 43 nickel, right. Now, you know what is the liquid composition and the solid composition. What happens to the weight fraction of solid and liquid? What is the weight fraction? The weight fraction of alpha in this case will be this distance divided by this total distance. What is this distance? Here 32 and here you have 35. So, that will be 35 minus 32 divided by, this is 46 minus 32. So, that is 3 divided by 14, that is the weight fraction of alpha. And now, if you calculate weight fraction of liquid, that will be, no, it is not 46, sorry, 43, this is 43, 43, this means this is 9, that is 1/3, that is 33.33%. Weight fraction of liquid will be this distance. So, that is 43 minus 35 divided by 43 minus 32. 43 minus 35 is how much? 6, sorry, 8, 43 minus 35, that is, and then divided by 43 minus 32 how much? So, this is 11, not, I am sorry, this is not 33.33%, 11, and this is by 11, right. So, we should always have W L plus W alpha must be equal to 3 by 11 plus 8 by 11, that must be equal to 1. So, it is working. So, this is 3 by 11, this is 8 by 11, that is the weight fractions. So, you can see now if you look at position B, the distance from the fulcrum point to the liquidus is 0. That means, that is actually represents the weight fraction of the solid. So, the weight fraction is solid is almost 0, there is nothing. By the time you come to see, the weight fraction of the solid has increased. That is what is expected to happen, right, because you are starting from a liquid state and you are cooling down, all the liquid has to slowly transform to solid, right. So, here you have 43 nickel and 32 solid solution has a composition 43% nickel and a liquid solution has a composition 32% nickel, right. That is how you can represent the microstructure. So, the yellow color represents liquid and the saffron or orange color represents the solid solution. And now, if you further cool it down just above the solidus line, again you are in the two phase region, and then you can see that it hits the liquidus at 24% nickel and the solidus is hit at 35% nickel. That means, at this particular configuration you will your weight fraction of the solid will be, what is the weight fraction of the solid? The weight fraction of the solid is, so this is the point, right, and all the liquid. So, from that point to the distance to the liquidus line, that is the distance. So, it is almost 100%, very close to 100%, just above this line. So, you have several alphas, the solid solutions, and some amount of liquid is remaining. Whatever alpha that is remaining, that has already got 35% nickel and remaining liquid has got 24% nickel. And the moment you come here, you are in the single phase region, all liquid has gone, everything is now alpha, and then we have all the alpha again has 35% nickel. It should come back to 35% nickel, because that is what is the alloy composition that with which we have started off, right. So, this is how the microstructure evolves. So, you have a liquid state and when you are cooling it down gradually, you are forming the grains of alpha, and it is possible that several nuclei might form within the liquid and each one of them grow independently until they meet each other and then form final grains like this. All right. So, we have discussed that alloy is completely phase. Now, let us look at what happens when we do this cooling in a non-equilibrium manner. What is the meaning of that? Please understand here one important point, when we are talking about being just above D in terms of temperature. So, just on the two phase region you have some alpha and some liquid, right, but then just below that, not only up to E, even here the microstructure will be same. As you are completely coming down, the microstructure does not change, all that changes is the temperature of the solid will change, the microstructure will be same even just below this guy. Okay. So, does that mean that from this state to this state it changes all of a sudden? No, there is a sufficiently long amount of time that is spent in order for the system to go from this state to this state. We are simply not showing the time in this phase diagram, there is no time in this phase diagram, right. So, from D, just above D to just below D, it could be several hours, which is not being shown in this phase diagram. So, when we are saying that we are just above D, we are looking at a time which is reached in equilibrium state. So, this is an equilibrium configuration. From that equilibrium configuration, if you reduce the temperature at a very slow rate just below D, and after sufficiently long time, you would have got structure like that. It is simply that we are not focusing on the fact how we are not showing the time factor here in this phase diagram. We will talk about the time in the next module when we are discussing heat treatment of steels, but here when we are talking about these binary phase diagrams, we are not showing time explicitly. All right, and when we are drawing these microstructures, the assumption is that the cooling is done in an equilibrium manner, meaning we have done the cooling in a sufficiently slow rate. That means the cooling rate is very, very low. Okay. So, what happens if you do non-equilibrium cooling? That means if your cooling rate is not as slow as what we have shown here, that means the systems did not reach their equilibrium configuration. If the cooling rate is high, the system do not reach their equilibrium configuration. And what happens if you have such kind of cooling rate, and what will that lead to the changes in microstructure. Okay. So, this picture represents the evolution of microstructure for non-equilibrium cooling. Here the two red lines, dashed line, two red solid lines represents the solidus and liquidus line for equilibrium cooling, and here what we are assuming is that in the liquid state the equilibrium exists, and the cooling rate in the solid only in the solid state there is no equilibrium. The cooling is done in a non-equilibrium manner only in the solid state, but not in the liquid state. That is a reasonable assumption, because in the liquid state you are doing at very high temperature, right. So, the assumption that the equilibrium exists in the liquid state is a reasonable one, but in the solid state you need sufficiently long time for solid state diffusion to take place. So, it is a time dependent process, and hence cooling rapidly is going to be detrimental or going to change certain things when we are looking at solidification in the solid regime, and hence there is no change in the liquidus line, whereas the solidus line, when we are doing non-equilibrium cooling, the non-equilibrium cooling solidus line is represented by this dashed line. So, now the microstructure should evolve according to this guy. All right, now let us look at what happens. Now, we have the same 35% nickel alloy. When we are cooling down up to point B, nothing changes because the liquidus line did not change, and again same small nuclei of solid alpha form, and the composition of alpha will be about 46% and composition of liquid will still remain be 35%. Now, let us say we are cooling down to C prime, C dash. Then if you draw a tie line, if you have done the equilibrium cooling, it should have got 40% nickel, but because we have done it in a non-equilibrium fashion, the tie line hits the solidus line at 42% nickel. And please keep in mind that this is 46% nickel, and here you should have got 42% nickel, right, because you are cooling at faster rate. But because you are cooling at a faster rate, the solid state diffusion does not have enough time. What should happen? See, initially you have got 46% nickel formed here. By the time you come here, this 46% nickel should actually change to 40% or 42% in some sense, 42%, right. But if you do not give sufficient time, there is no possibility for diffusion to take place from the solid state to the neighboring liquid state or the neighboring solid that is there. And as a result, what happens is the outermost layer will have 40% nickel corresponding to this, and the innermost layer will have 46% nickel, giving rise to an average. If you take, so that means if you have this solid, you will have this part has 46% nickel and this part has 40% nickel. On an average, this entire solid has 42% nickel, which is consistent with this. So, on an average you will have 42% nickel, but this 42% nickel composition is not uniform, right. This phase is not a uniform phase, non homogeneous phase, because you have at the center you have 40% nickel, at outer phase you still have 46% nickel. Sorry, I have done the yeah, at center you still have 46% and the outer phase you will have 40% nickel, right. This is here it is shown the other it should have been, this is 46% and the outer phase is 40%, something like that. All right. And now if you further cool it down, if you are at D prime, again normally you should have 38% nickel, but here also because the center one will still, maybe the center size that is having 46% nickel is reducing, but the next core will have 40 and the next one will have 35% nickel, but effectively this entire thing together will have 38% nickel. So, the phase is not homogeneous from the center to the outer. That means, the solid grains that are forming, they are forming like this with different percentages of nickel. So, this is 46% nickel and this is 40% nickel and this is 35% nickel, and together if you take the average of all these things, then that will be this entire thing will be 42% nickel. All right. So, normally if you are doing equilibrium cooling, you would have finished your solidification at this point D prime, but because we are doing non-equilibrium cooling, the solidification does not end at say 1220 degrees Celsius, but it happens at a much lower temperature, approximately at 1200 degrees Celsius. You need to come up to E prime and there you will have 31% nickel would have been on the solid state, but effectively you will have 35% nickel and hence you will have outermost layer having 31% nickel, right, corresponding to that. That means, the outcome, the microstructural outcome of this non-equilibrium cooling is that you will have a chord structure of your solid phase. The chord structure is again in a way that the outermost layer. So, that means, if you have the liquid and you have, let us say this is one grain, this is another grain, right. So, this grain like that and this grain also they meet like that, and these outermost layers are rich in low melting point alloy. So, here you see normally this should have been 35% nickel. On an average it will still be 35% nickel, but in here you also have regions of alpha which are particularly this one has 31% nickel. 31% nickel means 69% copper, as opposed to 35% nickel, 65% copper. That means, you have the low melting alloy getting segregated near the core, near the boundary between two particles. So, such a chord structure is an outcome of non-equilibrium cooling. So, this process is called segregation, and so the core structure, the problem with the, so that means that you have a higher concentration of low melting element increasing from the center of the particle to the grain boundary, that means the boundary where two grains meet, and such a structure is called chord structure, and this chord structure gives rise to inferior mechanical properties. Why? Because if you are heating a casting made out of such a system, such a chord structure, what might happen is the grain boundaries, because they are rich in low melting alloy, the grain boundary might actually melt first. So, if you are imagine using this component at high temperatures, the grain boundaries will melt. As a result, the material might actually give in, that means it might actually fail. So, the grain boundary region melts first, which is richer in low melting element, and that can be detrimental for actual service conditions. So, you need to do something about it, and so usually, however, in reality we cannot do equilibrium cooling. So, many times we will only do non-equilibrium cooling, but since we know that when we do non-equilibrium cooling we will have this kind of cored structures, you need to do something to eliminate this coring. So, typically all at the end of the solidification process, all the alloys are usually subjected to certain kinds of heat treatments. Here you call this as a homogenization type heat treatment has to be done in order to eliminate these core like structures. Okay. So, now let us look at the mechanical properties, how the mechanical properties, why are we doing alloyings, as we have discussed we can enhance the mechanical properties, right. So, if you look at the tensile strength of copper nickel system, you can see that the tensile strength of these alloys, particularly if you take about 60% nickel one, has the maximum tensile strength. So, all the alloys from this composition to this composition, from say 25 to almost 90 are going to give you a higher tensile strength than both copper and nickel independently, right. So, this is what we call this specific strengthening mechanism is called solid solution strengthening. So, addition of nickel and copper leads to increase in tensile strength and decrease in ductility. All right. So, with that we will stop here, and then we will look at some variations of type 1 alloys and type 2 alloys in the next class. Thank you very much.